Hello, everybody. This is lesson number 18 in Math 100. Lesson 18 covers the second part and the last part of chapter 7. And chapter 7 is all about math and art. All right, so today our focus is on math and music, music as a area of fine arts. Right. So in the background, you see a sort of a spiral thing, which, remember we have a reference to the Fibonacci sequence, how that is related to the spiral and the golden ratio. All right, so today this lesson is going to cover the last two sections of chapter 7. So 7.3, which is music, harmony, and the frequency of musical scales. And also 7.4, which is on fractals. All right, I'll be using a little app, and I don't know if you can see this. This is an app on a little piano, and I'll be illustrating what I will be demonstrating in terms of the piano, the musical scales and harmony. And so let's get started on math and music and math and fractals. Okay, lesson 18, section 7.3 and 7.4 in the book. And the topics are scales and harmony. This is music and how that is related to mathematical structures. And then a very quick discussion on 7.4, which is these geometric patterns called fractals. All right, so topic number 1, music and mathematics. All right, so what's the first name when you think of music and math? Well, years and years ago, and I'm talking about something like 2600 years ago, there was a famous person who sort of pioneered an area of mathematics as well as music, and his name is Pythagoras. Pythagoras. Now, what does Pythagoras have to do? He lived like 570 to 495 BC. So this is a long time ago, right? This is like 2600 years ago. The Greek mathematician who studied ratios, and he once told everybody that all numbers are rational. It turned out to be wrong, as his own theorem, the Pythagorean theorem illustrated. But he, thought that the ratio is where beauty is, and so he saw the ratios as philosophical objects, the aesthetic objects. And part of that ratio, of course, has to do with harmony, like what sounds or what pitches or what notes will sound nice together. And so that led him to the study of harmony. So in that sense, he's sometimes called the father, not only of the geometry, but the father of music theory. All right, and if you go for several centuries, maybe a couple of millennia, later, in the old traditions of university education that began in Europe, okay, we had the subject topics or the set of a curriculum called quadrivium. Quadrivium consisted of 4 subjects in higher education in medieval universities, such as ones in Bologna and different places in Italy and Spain. But those 4 subjects that all students studied were arithmetic, geometry, astronomy, and music. And what's interesting is that all these 4 subjects have a lot to do with mathematics. So mathematics was considered to be the subject, that would develop one's mind. And so a part of that, interestingly enough, is the musical education. Wouldn't that be great if everybody studied music as much as mathematics, right? That every school, every district, every state in the country would require everyone to study music as well as math. I mean, math is a mandatory subject for everybody. How about music? How about astronomy? How about geometry? Okay. Well, all right. So back to the topic of music, sound. Okay, music is about sound, possibly with silence, and sound is produced by air vibration, obviously, right? And then, depending on how that vibration happens, we can define what is known as the pitch. Of course, this is how high or how low. You can talk very high like this, or you can talk very low like this, right? And that pitch is determined by the frequency of that air vibration. How many times the string or air or whatever is vibrating per second, okay? So if you blow into, a trumpet or a woodwind instrument or something, that would cause the vibration of the air. And the frequency, how fast it's vibrating will determine how high the sound is. And so that is called the pitch. All right. So if you are a music student, and you don't have to be to understand the ideas of this lecture, but if you are a music student, some of these things will sound really, really fundamental. Okay. And here you can see a part of a keyboard or a piano keys, and then the corresponding notes, right? So this one is called C. And then you have, and piano is a sort of a C-based instrument, and then you have D, E, F, G, A, B, C, and these are not equally separated, right? So for instance, between E and F, there is no black key because these are half step apart from each other. And the same thing happens between B and C, that there's no black key right here or right here, okay? And I'll talk about this. Basically, there are 12 half steps from this C to the higher C, which is called 1 octave higher. I just use the word octave, and that is one of those main things I need to discuss. But let's say you start with a C, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and the 12th note is the next C up, right? So this is called 12 half steps in the musical scale. All right, so what I just did is to tell you from C to the next C. This is called the C major scale, right? And so what is a scale? Well, it's a span of musical tones or musical notes that go from a certain key to the same key higher level in the next level or octave. Okay, so what is an octave? You by the way, you notice here I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 letters to distinguish these notes. And so 8, the word oct has to do with 8. An octave is the span of musical notes in which, and this is the important thing, in which the frequency doubles. All right, so you can play the C at a certain frequency, usually like 260 or something. And if this C has a frequency of 260, and by the way, that means as soon as you hit the C, the air starts to vibrate 260 times per second. Now that's a lot of lots of vibrations per second, right? But it turns out to be a pretty low end of what we hear, because we can hear sound with a very high frequency, right? And in fact, very high frequency is called VHF, and ultra high frequency is called UHF, and those are both bands used by the television stations and so on. But this is 260 ups and downs per second, and we call this the units. The unit R, or the unit of the frequency is hertz, Hz. Okay, or it is the same. This basically tells you how many times the sound wave is going up and down, right? Or it's called cycles per second, CPS, and these are really the same units, right? So if this C has a frequency of 260, and that sort of depends on how you define the scale, then the next C up, this is the octave higher, the C an octave higher, it has exactly twice the frequency, which is 520. Now, this is another C here, okay? This is an octave even higher. Now, what happens if you double from here to here, and if you double again from here to here? Okay, it's not going to be an increase of 260, but you have to double this to 1040, okay? So an octave is defined as a span of musical tones in which the frequency doubles. Another way of saying this is that every octave you go up to, then the frequency doubles, okay? An octave is the interval of music sound in which the frequency doubles. A scale is a sequence of musical notes, tones, spanning an octave. And again, the word has to do with 8 notes, right? Most scales have 12 tones. And by the way, what I'm introducing you to here, or what I have been describing, is the typical Western scale. And depending on what tradition or what ethnic music you listen to, some of them have different, octaves and scales. Most scales have 12 tones with the frequency increasing with a common ratio. We will call that ratio R. Okay, now this should remind you of something we have studied in the past. What is that? Something goes up by a common ratio or percentage. This is exponential growth. Okay. Now, you first saw exponential growth, not in that section on exponential growth, but in compound interest. Then that's exactly a good point. Okay, it's a great point because the money in compound interest, the money grows exponentially. And remember things like, the population and the number of people infected with virus without any way to slow it down, they grow exponentially. And now we are finding out that on the musical scale, the frequency of musical notes grows exponentially. And it's the same mathematics that describe all of these phenomena, right? And that's what gives power to mathematics, because those mathematical patterns can be used to describe all sorts of things: money, population, and now musical notes, right? All right, so this is exponential growth, like money or population, doubling every 12 years. Now, why do I say 12? Okay, because remember, from this C to the next C, we have 12 half steps, right? And so, and we'll demonstrate that in just a second. One typical way to tune musical instrument is to start with an A, okay, with an A sound. And so let's say this is your A right here. Okay. All right, that's the key A. And you can tune, of course, you cannot tune the piano so easily, but if you're playing a guitar or some other instrument where you can just tune the individual, instrument, you can use this A tuning, which is to set the middle A to, okay, so many of you probably already know this, 440 CPS. And of course, CPS stands for cycles per second, as I mentioned a few minutes ago. All right, so if you tune it to 440, then what happens to this? Well, let's see what happens to that. Well, okay, so I'm going to let you do that in the in your worksheet, or maybe in your homework. All right, but for right now, okay, let's focus on setting this at C. All right, so another way, so the A tuning usually starts with A is equal to 440, but for this one, let's use the C tuning. What do we mean by that? Well, we start with C, and C, if you use C as your reference number, we let C be 260 CPS, all right, cycles per second. Now, here's the mathematical aspect of this. This will be the most mathematical part of our lesson today. Okay, so here's what we have. You start with C, and I say let's set this to 260, right? So once you go C sharp, D, D sharp, remember there's no E, there's nothing between E and F. So this is just a half step. So half step from here to here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is not right. So let me see what's going on here. Okay, sorry about that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the 12 steps up. 12 half steps up is another C, and this, of course, span is called an octave, right? So once you go from C to the next C, I said frequency what? Doubles, right? So it becomes 520, which is 260 times 2. Okay, so using this tuning here, and it really doesn't matter what tuning you use, but if you use C equals 260 as the beginning point, this is what we want to do, right? Remember, you add to get to the next frequency. All you have to do is to multiply this by 1 plus the ratio. Okay, if this ratio is 10%, you just multiply this by 1.1. You remember? If this is 40%, then you multiply each time by 1.4. Okay, and so you have this common ratio R, 1 plus R is the thing that you multiply by to get to the next frequency. And if you go the 2 half steps or 3 half steps or 4 half steps, all you have to do is to use that as your exponent, right? And what we are saying is, if you start at 260, and then if you have 1 plus R, and this is the factor by which you multiply, and if you do it 12 times, remember, this is exactly like your exponential function equation or compound interest equation, where the compounding is annual, right? So this is like 12 years of compounding, the money compounding with an annual rate of R, starting at $260. Okay. So what happens after 12 years if you deposit your money, $260 at the rate R? Well, according to this, you want this to be doubling every 12 years. So this becomes 520, right? If you divide both sides by 260, okay, all you get is 1 plus R raised to the 12th power is 2. Okay, this is, 2 means it's doubling. And so you can actually solve this by taking the 12th root of this. Now, you don't have to know this. This is very high intensity algebra, sort of. Okay, 12th root, it happens to be 1 over the 12th. This is the exponent to the 2. So it's really 2 to the 1/12th power. Okay, and so R happens to be this thing, the 12th root of 2 minus 1. Okay, and you don't have to know this all the calculation, but what I do want you to know is that this R turns out to be just about 5%, 0.059463 dot dot dot. This is an irrational number. Okay, it is approximately 5.9% or 5.946%. What are we talking about? Okay, this is the number, this is the rate or the ratio by which the frequency increases every time you go to the next key in the piano. So from C to C sharp, what is the frequency of C sharp? You take this number and multiply it by 1 plus 0.059463, right? And so if you do that, right, so here, let me just go ahead and erase these, and I will show you how to fill these blanks. All right, so since you have studied compound interest and exponential growth, we've experienced this twice already. So starting at 260, what's the next number here? So this will be the frequency of the sound or the tone half step up from C, which we call C sharp. All you have to do is to take 260 and multiply that by 1 plus this number R, which was 0.05946 and so on. So enter 260 times 1.059463 blah blah blah. This number should be in your memory if you know how to do that. It turns out to be 275.46. Okay, and then if you take this number 1 plus that R and square it, multiply by 260, this will give you 29184. Okay, and you can continue to do this. For E, you will get 32758. Now, what is that? 1, 2, 3, 4. This will be 260 times 1.059 blah 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 to the 4th power, right? And for the 5th power, you have F, that's 347.06, okay? And then this is the 5th, 6th, and 7th. This will be 260 times 1.05946 to the 7th power. And that's going to give you the frequency of G if you are using the C tuning, all right? And so after you calculate bunch of these things, and I will have you do this in either in your worksheet or on your homework or both. Okay, but if you do that, by the time you get to the 12th power, okay, that's 260 times 1.059463 to the 12th power, you will get exactly 520, because that's how we found out that number R. Okay, so for the music theorists, this really is the key that controls the musical scale that we use for like pretty much every type of music that we listen to and we play and we compose. Okay, 5.9%, 5.9463%. This is the magic number that separates each half step of our piano key, right? And so, and you know the difference between C and C sharp, right? Or E and F and so on. The difference is significance, and the difference, mathematically speaking, is only really about 5.9%. Okay, and I find it pretty fascinating. Now, the reason this is such an important concept here is not because we can create our chart like this, okay, but based on these, okay, we can tell which sound will sound better together than others, okay, and so that would be the next part of this video. And so next time we'll talk about, in the next page, on the second page, we'll talk about harmony and consonant and dissonant sounds and so on.